All right. So we are going to do hands-on using the agentic patterns that we have seen here. So we're going to start with the React pattern, and then we'll also do the plan execute pattern, and then the two augmented RAG. So let's just go straight to it. I already have a Jupyter notebook, which I have started a bit of that, and I'm just going to bring that notebook across. I'll share this later on. Okay. So React, like we said, this is not React. This is not the JavaScript React, right? It's not JavaScript React. It's um, reasoning and act. And if you remember, when we were looking at that pattern, just as a um, quick recap, we are talking about agent reasoning patterns. So when you're building agents, agents are really suited for tasks that the steps are not very clear. So at the point you are writing the code, you have not yet defined the steps, or the steps cannot be defined because it's dynamic. Maybe the steps would depend on what inputs are coming in and all of that, right? So that is basically the agentic use case. If not, you can use a chain. If the steps are very clear and you don't want any change in the procedure midstream, right? So you can then do a chain, right? But an agent use it for things where the steps may change depending on the inputs that come in or the context and all of that. So use an agentic approach. And in the agentic approach, of course, remember, agent has the main components of the agent. Of course, you have the LLM that does the reasoning. Then you have the tool that allows you to take actions, or allows the agent to take actions and do things, right? And then the other things, well, everything kind of comes under tools, right? It's really basically an LLM that is powered with tools. But the third part of what makes an agent is the pattern that allows it to recursively, not recursively, iteratively rather, continuously um, cycle through this loop, right? And um, the React loop is one of the first patterns that you use, which is the agent will analyze the current state and analyze the task that it is given, and then decide the next best action. And that action could be to either call a tool, which you would have provided along with the agent definition, or um, you know, it could actually just give you the outcome immediately. But if there is need for a tool, then it will request a tool call, and then it will observe. So the third step is observing, where it waits to get the feedback from the tool call or the result from the tool call. And typically that result is still sent as a message, what we call a tool message, in LangChain. And then it takes the result from the tool call and again looks at the history of the conversation. It looks at the original request, the original task, and if that is sufficient to give an answer, it gives an answer. But if it is not sufficient, it will think again around it and make additional tool calls. So you now have it, kind of repeatedly cycling in a loop until the agent is able to come up with what answer that it needs to give, and then it terminates and gives the final answer. So that's the cycle, right? So that's basically React. So we are going to go look at how to implement it, right? And it's actually quite simple. reason, and act. 2 steps. The first one is to think about the problem, and the second one is to take an action. So with LangChain, it's very easy. LangChain has this create agent method. So by the way, for your information, if you're using LangChain version 1, there have been a lot of changes. So sometimes if you are using AI generated code for LangChain, especially when it has to do with agents, when it has to do with context, and when it has to do with states, vector databases, you may end up with really old, outdated code. Unless you are using an older version of LangChain to run it, that it will still run. But if you're using a newer version of LangChain, most of the LLMs currently, if they generate code for you, it will be wrong, basically, based on recent, improvements. So it's always a good idea. Go check LangChain documentation, right? I think LangChain even has, um, there's a version 1 um, change log, right? A version 1 change log, or V1 change log. Let me use V1 that kind of specifies some of the things that changed, right? So I can share the link to the change log. This is where it is. Let me post that link here. So you can go check it out. But I would encourage everyone to basically just study LangChain very well and understand how to do stuff. This is the link. So the way agents were created before has changed. Before it was always create React agent. This create React agent was basically LangChain's way of creating an agent based on the React loop. That is the reason and act loop, right? That's why it's called create React agent. But that was before version 1. Now we just use create agent to do that. And create agent is going to create an agent based on the React pattern. So the React pattern is the default pattern that LangChain will use to create agents, right? As you can see here, create agent is built on the basic agent loop, where you call a model, you let it choose tools, and then you finish. So once you do this, you don't need to manage or babysit that process. We can talk about middleware later on when you are creating agent that you can influence the things that go on by using middleware. But that's not for today though. So yeah, so we get from LangChain agents, you get create agent. Then from LangChain tools, you import tool, right? Tool is just an annotation, right, to annotate the tool. So we now have a tool to get exchange rate. And then we now use create agent to create the agent. Before we used to have this agent executor, right? Which will create an agent and give it the list of tools, but that is no more used, right? You don't do an agent executor anymore. Create agent handles that under the hood. So what you simply do is agents.invoke, right? You invoke the agent and you pass the query. Of course, we have to create chat OpenAI. It is LangChain OpenAI. I'll need to install this because it doesn't come with the core LangChain. By the way, in your Jupyter notebook, the core LangChain actually is installed in the runtime environment, but the other things are not installed. So in this case, I have to pip install LangChain-OpenAI. And well, install OpenAI as well. Even though I don't really need to install OpenAI in a Jupyter notebook environment because it's already pre-installed, but I still run this to install both the LangChain OpenAI. If it's Python, if it's JavaScript, you would use something like npm install at langchain/OpenAI or something like that. So we are going to look at how to do that in JavaScript as well. So once we install this, then this becomes available. So the chat OpenAI, which is the model, the OpenAI large language model, using the OpenAI SDK. But of course, I always like to use the um, Open Router in this case. So I'll use the NVIDIA Nemotron and Open Router as usual. I'm going to do this really quick. So I'm going to copy it from there. Then the other thing is the temperature is there. I'm not going to specify any other thing, but I will specify that I want to use Open Router. So I'll specify Open AI API key, and I will get that from the environment. Okay, and Open API key, and then I'll also get the um, um, API base. All right. So that's the base path to the Open Router API endpoint. So that is typically openrouter.ai/API/version1. Okay. So of course, this means I have to bring in my .m file. So I'll create it now. And then let me go look for the Open Router API key quickly and put it in here. And this really makes it very easy. LangChain makes things very easy. So we had already kind of done this, right? When I was going through what LangChain does. So I'm really just explaining something we had already looked at. Remember when we're looking at agents, we actually looked at it. So um, yeah, of course, I have to, let me pull all the imports into a separate code block and then also add the OS and the .env, right? So of course, once load.env gives you a true, that means it has seen the .env file and loaded it. And then we load this. So we would define tools. So we define this tool, and this comment is always very important because this is when LangChain is processing this tool to generate the tool schema to send to the LLM, it actually uses this comment as a description. So this informs the LLM of what this tool does. So it's very, very important. And then of course, LangChain is going to pull the tool signature from here to know the arguments or parameters and the type of the parameters and the return type. So this is what really makes LangChain so powerful. You don't need to do all of that manually like we were doing before when we were learning it. So now I go to Open Router. Let me look for Nemotron. Um, Let me look for Nemotron. I think I can use this Nano A3B. So just click on this to copy the model ID. And so that sets up our LLM, right? And this sets up our agents. So you see the 3 steps. This sets up our tool, this sets up our LLM, and then this sets up our agent. And we call the agent, we tell it what the LLM is, right? By the way, this should be model, not LLM. So the name of the parameter is model. And then the name of this one is tools. So that one is correct. And it's always a list. And then we can invoke. So remember, when you invoke an agent, it's going to give you a list containing the entire conversation history, right? Um, okay. Yes. So I missed something. Again, this is part of a case of I generated this from an LLM, but the API, the way it create agents is the way an agent is invoked is different, right? Model and tool. But the way you invoke it, you have to go down a lot, down to the bottom to see this. Um, you you pass in the prompt, right? Um, you pass in the prompt as messages. Essentially, you send it a dictionary that contains all the data, but the messages that you send it as messages and you send it as and the messages itself is a list. That's how you trigger it. So this is the old way of doing it using inputs. So what you do is you send messages. I could decide to come to turn this string into a human message by just saying human message, right? This is very explicit because at least this tells LangChain that okay, the first part of this is a human message. Of course, I have to get human message. I have to import it from the langchain.messages class. So from langchain.messages, you import human message, right? So this is one way of doing it. But interestingly, if you do not specify the message type, LangChain will automatically um, kind of cast it for you. So it's going to convert this into a human message. So it's still going to come in as a human message, you can see, even though I did not specify it to be a human message. So there's that flexibility. But I could also have decided, okay, this is a human message. So let's specify this as a human message. Okay. And you know, it does the same thing basically. So LangChain is going to put all this together. So you can see the response you get, the messages. Um, you have the human message, which is the first that was sent. That is this one. And then you have an AI message. So again, the AI message has no content. So when an AI message doesn't have a content, it's most likely it's a tool call. It's requesting for a tool call. So it doesn't send any message back. Rather, it will send um, a tool call, right, which you see here. It's going to tell you the list of tool calls. So by the way, the finish reason is another interesting thing to look at. Why did this LLM, what made it stop reasoning and send you a response? That's what finish reason is. And in this case, finish reason is um, tool calls. Again, I need to figure out how to properly format these messages so that it's easy to see, but I'm going to look for a tool that does that. Anyway, so finish reason tool calls means that it basically needs a tool call. So it has stopped reasoning and is sending a response, right? And that's why the content is empty, but it gives you this tool calls list, right? The tool calls list tells you these are the tool calls I need, and it's a list as you can see. And it gives you all the tool calls. Right now, there's only one tool call, the get exchange rate, because the prompt was convert 1,000, 10,000 naira to USD. So because you had defined your get exchange rate as a currency, and your definition says it will give you USD exchange rate given the Nigerian equivalent, right? So it's going to format the tool call, and in this tool call, you will see that the arguments it just gives is the currency should be in Nigerian naira. This is not a very good tool call definition, by the way. If it were me, I would define this like um, from currency and to currency. This is the best. So let's do it that way. So from currency and to cryptocurrency. Okay. And you know, so this just assumes it gets USD. But anyway, the from currency to currency is nicer because then I could decide I don't have to hard code the USD. But anyway, this is just for purpose of demonstration. So let me minimize the complexity and leave it at that. So it sends the arguments, as a tool call, and you now see that LangChain automatically, your agent that you have created in LangChain is going to automatically um, invoke and execute that tool call. It's basically going to call this function and pass in the parameters. And the result that comes from it, it will create a tool message and send it back, right? So you see that the tool message, the content is 0.00067, which is the return value from the function call. And then, of course, you have to specify the name of the tool call so that the LLM will know which of the two calls it specified this one is addressing. And that's it. So with that, then of course, remember all of this is going to be injected into prompts and everything. And then the AI message will it will give you a response, which is based on the tool call. And that is it. So you can then pull the content from it, right? And that's it. These are additional metadata if you want to use it to analyze. So that's more advanced stuff anyway. So of course, remember I use Markdown. So import from dot display import Markdown. I don't need to import display again. I just need to import Markdown. So I can then print the Markdown version or the Markdown, decoded version of the message. Okay. Oh, by the way, I did not assign this to something. So let me just say response equals this. So I can rerun it. And then it will be response. So remember, response is a list. Response is a structure. It has messages in it, right? But the response messages is a list of all of them. And we want the last one. That's the final response. So we use -1. And then we get the content from it. And that is it. So you see the response here. The current exchange rate for one NGN to USD is this. So to convert 10,000 NGN to USD is that, which is 6.70 USD. And that is a simple React pattern. Now, the question you will ask is, this was a simple case because it didn't need to loop, right? The agent didn't need to loop. So I'm going to look for a problem and I'm going to bring up a problem that requires, after the tool call has come back, the agent still needs to maybe do a second tool call, okay? But while waiting for that, I'm going to run, I'm going to run, um, I'm going to run a JavaScript code, but let me still do this in this browser in a code space, a GitHub code space. So GitHub code spaces are really nice because it allows you the same thing I'm doing with the Colab, right? I can do in the GitHub. Most of the time, if you have an account, you have a limited amount of code space units. And I think I may have run out on my code space units on this particular account until they reset my usage by the end of the month. So I'm going to use a different account where I can still access code spaces in there. So let me pull that one up shortly. Give me a second. Um, I could also have easily done it with my um, VS Code, right? But considering that Code Spaces also runs on VS Code, so it's not a bad idea. Okay, so I have a new code space which I have created. There is nothing in it at this point. Um, I am going to um, open the code space here. Okay, so um, okay, so I have this. Um, if you want to open code spaces in GitHub, you just click on this menu, you will see code spaces. And yeah, so I ran out of my uh, code space budget, basically. So what I'll do is I'm going to switch to another window where I have created this new code space just to do the same thing um, that I just did, but I want to do it this time around with JavaScript. So, okay. So this is a repo I just created. There's nothing in it. Okay. LangChain agent. So we'll start with a simple React agent. So I'm going to create a new file, React agent dot TypeScript. Remember, in LangChain, you have to do a bunch of stuff. So you have to install LangChain, you have to install, I'm going to use PNPM. Code spaces normally should have PNPM, so I hope it does. Good. So it has PNPM. It also has NPM, but I prefer to use PNPM. So I'm going to PNPM install or add, for PNPM is the same thing. Install LangChain core. Okay. So we need LangChain core. Then we need LangChain. Um, there are three imports. So let's look at the code. I'm going to take this code basically, and LangChain core contains the tools. Okay. Then LangChain core also contains the we'll have to get LangChain messages as well. So PNPM install LangChain messages. Um, messaging messages. Um, okay, messages is probably in core and agents as well. So I'm just going to start writing the code for this in JavaScript or in TypeScript, same thing. Okay. Okay. All right. So, of course, TypeScript, you do imports. Um, so we need to first of all get the oh yeah, I forgot. We'll need to get the OpenAI. So let me paste the code I copied. This is the Python version of the code. So just for me to use as a reminder of what I need to do. Interestingly enough, VS Code has an agent that we could use to just translate this, but I'm not going to do that. So we need tool, and we need OpenAI. So for OpenAI, we need to install LangChain OpenAI, like we did in the Python version. Um, so take a close look at my terminal. I can't really bring it up, or maybe I should clear. Let me clear so that it's easy to see what I'm doing up here. So we have to install the OpenAI. So LangChain OpenAI. Okay. We also need to install um yeah, so okay. I think that's it. So to get the tool, we need to import the tool. So import tool, right, from LangChain core. So tools are in LangChain core. Uh, tools are in LangChain core. Then we'll also import the chat OpenAI. This is also in LangChain OpenAI that we just installed, right? Okay. Then what else we need? We need create agent. So create agent. Um, that one is from LangChain for agents. Okay. So most of the core stuff are now. Oh, I'm sorry. This is supposed to be create agent. All right. Create agent. Okay, I'll wait for that to catch up. If not, I'll have to check it. All right. Um, so in JavaScript to define a tool, unlike in in Python where you can just use this annotation, in JavaScript you have to declare it. So you do const get exchange rate. So we define the function and we surround it in this tool, the tool function call. So basically what we are saying is that this thing that we are creating is a LangChain tool. Then we do the actual implementation of the tool, which is what we are doing here, right? I could take this and just dump it in here and do some code around it. So async, um, so you always put the parameters as the structured object, right? So um, it's kind of a convention because we also have to define the type as well. Currency of type string, right? That's a TypeScript type. And the return value is a promise and a number. Okay, so that's it. Then this is the actual implementation, which The actual implementation, we can basically what we did in Python was to define a variable, a dictionary that contained it, right? So in JavaScript, the same thing. We can say rate equals, it's also a dictionary, right? ngn equals, and this is the value. So that makes it easy, right? Then we can now return rates dot um, rates currency. This is basically the same thing as a Python. If it doesn't exist, you return zero. So this double pipe is to say, okay, return zero if this doesn't have anything. Okay, I need to specify the type here. This is basically a TypeScript thing. Okay, so um, the type, you can use a standard record type and specify string number. So this is saying, um, yeah, so this should go away. Okay. So this is first of all the function that will that corresponds to the tool. But this tool function, right, from LangChain needs two arguments. The first one is the function itself, right? And then the second one is okay, let me see if I can see this. It's kind of not letting me see everything. But the second one should be the schema that corresponds to this tool, right? The tool schema. So because unlike Python, where the metadata cannot be extracted directly from the function, we have to manually provide the metadata for the function call. So in this case, get exchange rate. Notice how we still use the same name, even though this doesn't match this function name, right? But we still use it. So the reason for this is that um, we could still use this name, right? This camel case version instead of this. It doesn't really make a difference, but in a way, the name here doesn't necessarily need to match a function name, but it's good to have consistency across board. So if I implemented this in Python and I implemented it in JavaScript or TypeScript, the LLM will still kind of see that it's the same thing, right? It's the same function. So description is USD exchange rate. Okay. And then schema. So schema basically would be a hierarchical stuff like this. But in TypeScript, in JavaScript world, there is Zod, which really helps in defining schema. So we can use Zod in this case. Okay, so let's use Zod. I'm sure a lot of the JavaScript folks know how Zod works. So use Z dot, and then we'll specify the schema. So it's basically a way of doing the type schema. So object, and then in this object you have currency, which is the arguments, right? The parameter that goes into the function call. Currency is a string type, result string. And then you add additional description for it, describe, and specify codes, right? So in a way, you see how it's a bit more verbose, right? When you're using JavaScript, because you have to do the definitions here. You have to define the schema while in Python, the schema is taken directly from your function definition. So let's install Zod. So pnpm install. Okay, so we still have to work this out. So we'll call create agent. We've done the tool, so now we do the LLM. We could actually just borrow this straight up and constant LLM equals chat open AI, right? Which is this. Now we'll pass in the parameters. So of course it's passed in this manner. It's a destruction object. So we'll still specify the model. And in this case, I'm still going to use my NVIDIA Nemotron. We'll specify the temperature. In this case, I'll still say temperature is 0. Then these other ones in JavaScript, we use camel case, right? Rather than this snake case. OpenAI API key. That's how we do it with JavaScript or TypeScript. And then os.getEnv, we use process.env. Of course, this means we have to install the .env library as well. Okay. Then we have configuration. So this is slightly different now. This is something I need to test, and base URL. So this is configuration for the OpenAI client. And the OpenAI client does have this base URL as one of the parameters that it takes. Okay. All right. So I may be missing something here. Okay. All right. So this is our LLM. Okay. So we now create the agent. To create the agent, same thing. We use create agent, and we specify the LLM. So I need to check this, right? We pass this in. Model is the LLM. Tools is this. The tool that we have defined, right? And then that's it. And so to run our agent, we will const response equals await agent invoke. So of course this has to be done in invoke, and we will specify the entire thing. Messages again, convert this to a JavaScript object, and this is the list of messages, which I think we can put it here. We can either just do new human message, or we can just pass that in. Again, LangChain is going to do the necessary conversions. And that's it, right? So this is our complete implementation, converting it into JavaScript or TypeScript. All right. So it's telling me that create agent does not exist. Yeah, so this is a new object process. Uh, Surprise is telling me process doesn't exist. Okay, so let's fix this. LangChain should have create agent. So it's very easy to fix that by just checking LangChain. Um, let's go to LangChain. Let's go to the LangChain, um, go to their documentation and so you can see that you have documentation for Python and you have documentation for TypeScript. So it makes it easy, right, for you to look at that. So we're going to look at agents. So you can build agents. Well, you have deep agents and then you have agent harness. Um, well, let's just do a quick start. Um, right. So LangChain agents is what I'm looking for. So you can actually switch between Python and TypeScript. If you want to go to their documentation, it's easy to switch it here. So in TypeScript, you can then see the implementation. So so you just get it straight from LangChain, I guess, not all right. So that is the mistake. I guess agent has been promoted to like a first class um part of LangChain. So npm install. So it's all LangChain. Right. So you have Zod and you have LangChain. So you really don't even need to go into this according to their latest documentation. Since documentation keeps changing. So what I'm seeing here is that you can do create agent and tool directly instead of going into this, right? Um, yeah, this is an old thing. And when you are defining the tool, same thing we did, you define the function and then you specify the schema of the tool schema. And Zod is really helpful for you to define the tool schema. And then you just create agent. There are two ways you can do this. You can specify, right, the model. When you want to specify the LLM, you can specify the model by using the name of the model, right? But in this case, when you specify the name of the model like this, what you're asking LangChain to do is it will look for the provider by itself. And so, for example, based on Cloud Sonnet, it will go look for it in Anthropic. Okay. Um, but sometimes it may not find it. Sometimes it will tell you the provider. You can try this out. It will tell you something about the provider not being available, or it doesn't know the provider or something. So the other way is you yourself create a model like this, and then you pass in the this right as um so with that it's able to use the model that you created, like what we did here. And that's it. Okay, so I need to inject this. So to inject this, create a .m file, and I'm going to open it. I'm going to put in my I'll probably just put in all of them. So I'm going to put in my um different API keys, including the open router one, right? Then we need to install .env as well. So import um, config from .env, right? And then we just run config. So once you do that, let's see, pip install config. Oh, I'm sorry. It should be pip install .env. It's .env I want to install. Okay. So with this, I can now run my TypeScript file. By the way, you can't run TypeScript file with nodes. You can't just do nodes React agent.typescript. Node doesn't know how to run um, um oh, I'm sorry, I did the wrong thing. Not pip pnp install.env. With pip, I just install with Python. Okay. So if I run nodes this, it okay, so it did try to run this, which is nice, but we now have no auth credentials. Okay. So let's see if I specify the .m file here. All right. Okay. Cookie authentication. Um, yes. So this is not. Let me confirm if I'm getting this process. Sometimes the javascript.env does not work as seamlessly. Having a bit of slowdown. Okay. Um, all right. So let me just run it again. Node React agent. Okay, so um module type is not specified. It doesn't pass as CommonJS. All right, so let's add type module here so as to make things simple for me. Okay. Um, okay, so I actually do have the correct thing here. Um, but it's giving me a 401 and it's saying the model authentication is not working. I'm probably missing something in this. Um, Probably because of the approach I have used. We don't really need this, I think. So anyway, I'm going to come back and look at this. This has to do with authentication, and I will fix it. But uh, essentially, I'm just trying to demonstrate that this is typically how you do it in JavaScript, right? Um, it's the same process. You create a new LLM, then you use the create agent from LangChain, you import it from LangChain. Of course, the OpenAI specific, if you want to use Gemini or something else, then of course you would import LangChain Grok or LangChain Gemini or whatever, right? And then put in the necessary API keys. So I have a feeling that I did not get the right configuration here. So I'm going to go check that out. But that's a process of doing this. I've not done this with JavaScript before, so I would expect that I should be able to pick this configuration, right? And the OpenAI API key is also correct because it has been printed out here. Oh, Open Router. Yeah, yeah, it's correct. SKORV1. That is what I have in here as my Open Router, so that's correct. So I think there is a little bit of a problem. We'll come back to that. Basically, model authentication. So this is how you do it in JavaScript. Okay, let's go back to the Jupyter Notebook, and I'm going to now show us um, additional patterns that we would be dealing with, right? Okay, now if we had, um, I kind of showed this the last time, right? But let's look at the plan execute pattern. Plan execute pattern, you would have a planner and then you would have an executor, right? You would have a planner and then you have an executor. Then you create a planner execute agent, right? And this is basically how you would do it, right? The standard pattern that we have been using, what we have been doing, that is the React pattern. And most models are already trained to be able to do that, right? But plan execute pattern is, it will first of all list out the things it needs to do, right? And then it will then go step by step to do each of them. So let's see how this will work. So let's start. Again, we need to define tools, right? Um, pip install chain experimental. So this kind of so there is a longer way of doing plan. Maybe I would break that down. It's pretty long, but I'm not going to do this. But LangChain kind of has created an experimental package that um, simplifies by um, bringing all of those in. Okay, so all of that is in the LangChain experimental package, and the LangChain experimental package allows us to LangChain experimental plan and execute package allows us to basically bring in a few classes that does all of this for us, right? Because if not, we would have to write the entire sequence of plan and execute. And I'm going to give you some sample code of how that would look like if we were writing it by ourselves from scratch, right? So, but this is kind of very simple way of doing it. Let's see how this works. So in this case, you import plan execute, which is basically an agent that has plan and execute implemented in it. Then it has load chart planner function that allows you to use an LLM and decide which LLM you want to use as a planner, right? In this case, it's still the chat OpenAI that we created here that we will use as the planner. And then you also use the load agent executor to specify which LLM you want to use to execute the plan. And then you also specify the tool calls. Okay. So once you create those two, then you pass those two in to the plan and execute agent. So the agent will know which LLM it wants to use for planning and which LLM it wants to use for execution. And then after that, you just invoke. Okay. Now I think yeah, I need to pass. So let me use this LLM which we had already created instead of trying to pass in a new open AI. So I'll just use this one. I'll use the same agent again as the executor. So, and I didn't define any tools, but you can define tools, right? That it may need. So I could define tools. The same way we define tools, you can define tools and pass them in here. And it's as simple as that. But the interesting thing is, like, if we really wanted to look at the code, right? If we really wanted to look at the code, you see that there is a lot. Okay, so yeah, you can see it gives us input, analyze Nigeria's fintech system. Output, it gives an action. Action is search. The action input is Nigeria fintech expert interview survey. Okay. And well, that's all it gives to me, which is pretty interesting. Now let's assume that I had defined, let me define two calls for it because I did not define two calls. So let me just let me just bring in the two calls. So you have a tool call that does search for fintech information. They have another tool call that gets market data, right? So and then I already have the LLM, which will just reuse this one that we had created here. So that's it. Plan and execute, planner, executor. Let me add something here to allow verbose. So verbose equals true allows us to be able to see, it prints out more information on what it is doing. Then we can pass this to a result object, and then we can view the result object. Let's pass in the two calls as well, which we just created. So we would have search fintech and get market data. Okay. Okay. So because I put in verbose mode, it's now kind of giving more details on what it is doing. So it breaks the task into steps. So you have all the steps here. Um, well, I think there's just one step, which is yeah, it just defined only one step. It's pretty long though. So it defines one step and you see all of this. And you now have end of plan. So it's essentially step value given the above steps taken. Please respond to the users. So the planner is kind of just a very well written prompt, which you could have done by yourself. And I'm going to show you code of a sample plan and execute how it would actually look like if you were implementing it by yourself instead of using LangChain's experimental plan and execute. It's good to do it by yourself so that at least you understand how it works. So remember, all of this is really about prompts going on at the background. And then, so verbose allows you to see each of that. And then the execute phase, after the planning phase, you now have the execute phase where each of these phase corresponds to a prompt that is sent back to the LLM. It does, and it gives you an action and then the action input. And then the next one, action input. Next one, action input. So each of the steps are broken down into actions and then the input that goes into it, right? And then after that, right, that's the whole plan. Okay. Then after that, that plan will be executed, and then you also get the response. So um you can see it's even a chain. So it's complete chain. You can look at the output by viewing the results output, right? And you see the output here. And you see the output has action, final answer, action input. So if the action is the final answer, as it is in this case, then you can take this action input and that will be the final answer. You can do markdown on this, results, output, um, action. The output is actually text, right? Um, which you need to JSON. I don't know why it's showing me this as text, but let's see, action input. Yeah, so result output we need to JSON load string and um yeah, of course, let's add JSON, import JSON. So this is finally what you get from that summary of Nigerian fintech landscape. So these are just examples. I can't really go into so much detail because of the so little time we have, right, to look at so many things. But yeah, so LangChain allows us to do this, right? You can pass two calls to influence what comes from here. But this would be an interesting thing for you to look at. Now, let me show you a full implementation if you were doing it yourself, right? So look at this. You have well, this is still using the old version. This is LangChain Classic. Um, so prompts, LangChain agents. So you define the tool. Um, this is create agent. So you define a tool, you have a search tool that you define. you have a calculator tool, you have exchange rate tool, right? Then you define your plan, which is a class, and the plan has to have steps, okay? And that's it. Then the response also has response. Then the act. So you have the plan and the execute. So you have the plan, and then you have the action that needs to be taken. The reason why this is defined with Pydantic is to ensure that you have validation. Then you create a class called the planner agent. It will have a plan method. So in this case, what is actually happening under the hood is a prompt is written that gives the objective, which is a task that you want it to plan, and then the previous context, right? And then the prompt is basically saying create a number list of steps to accomplish this objective. So you see, that's how plan and execute is. It's still a prompt that you give to the LLM. The LLM still does the reasoning and now generates the list. So we now invoke the LLM with this prompt, okay? And then the response that comes back is passed into the steps. Since you have given the LLM a format in which it should provide your response, right? You then take that format, you split it, and you will have the steps. Okay. Then this is just cleaning of the whole thing. Okay. Then once you get the steps, you return the steps. If not, you return the original content. So that's the planner agent, basically. Then the executor agent, again, you initialize it. You have a prompt template that we create from messages, and the messages, you have a system message first that gives the baseline in terms of the system agent. And then you have a messages placeholder, right, which is to contain the chat history. This is again when we're talking about um, memory and storage, right? We use the messages placeholder where you can use to pass in you know messages or the entire chat history, right? Then human basically human input. This is human message, and this is the input that comes in, right? So it's a placeholder again, and then you do placeholder, which is the scratch pad for the agent. Then you create the agent, right? Using the LLM and specifying the tools. Okay. Typically, yeah. Okay. And then the system prompt. Then you run the agent. I would say self.agent here. So you pass in the model is self.llm. Okay, tools is self.tools, right? And okay. So when you want to execute this step, you take this and then self.agent.invoke, and then you stack the messages here. So remember, we will stack the messages, and this is a list of messages. So the first one is the one we already have. Okay. So it's going to be this. This prompt is already a stack of messages. I would even rather have done this here. So this is another way you can do this. Let me take this off. when you are executing, um, you have all the messages here. So this can just be a system message, and that's the whole system message. Then message placeholder, then the human message with a placeholder. Um, right. So you stack all the messages, and the final one is the text, which is still another human. Okay, we have this already. So basically, you stack all the messages into this, and um, you invoke the agent with that. And the result from the agent, that's you can um, basically the result contains all the messages. Okay, so messages minus one. And that's it. So plan and execute agent will now combine the two. So essentially, I'm not going to go through all of this to the end, but the plan and execute agent is essentially prompt driven, right? And you could implement it by yourself. But LangChain kind of already helps with that by providing, see how long this amount of code is if you had to do it by yourself, right? And you have to tweak a lot of things and make sure things work. But LangChain makes it very easy by just allowing you to use this experimental class, right? Plan and execute. You get the plan and execute agent class. Then you have two functions. One allows you to load the agent executor and the other one load the chat planner. And that's it. So with that, I think I will pause and let's just quickly look at. Okay, sorry for that interruption. So we are going to talk about state memory context management. We kind of already talked about it before, right? So we are going to more or less write code samples. We're not going to do too much of um, theory this time. We'll just see how we can um, do simple state management. And then after that, we'll we're going to look at how to implement simple backends, right? For those who are Python, we are going to implement simple backends for basic workflows using this React, reasoning, retrieval, and so on. So we're going to do just a bit of hands-on. But yeah, let me just go through state and context management. mean that if you were to ask an LLM a question now, send it to the LLM API, right? We did that already when I was um, kind of demoing LangChain and LangChain state management. Okay. You ask a question, you tell him, hey, hi, I am, XYZ, and it acknowledges you. Then the next chat, who am I? It won't remember because it's stateless. It does not keep track of anything. Every prompt you send to the back end LLM is independent. Now, but in the real world, you need continuity, right? When you are chatting with ChatGPT on that user interface, right, that history is not actually maintained by the LLM, the backend. It's maintained by the app that is, it's keeping track of it, right? So LangChain helps to do that. The agent, class or the agent object that you create helps to do that, right? So the chat history that we have when we are chatting with, LLMs, the multi-step reasoning that we just looked at, react and plan and execute, and all of the others, right? They all need history, right? Even the user preferences, like things you have configured before. If you are writing an app that is based on LLMs and LLMs being able to reason, previous preferences and so on, and even ongoing task, all of this need some kind of storage, some kind of memory, some kind of context, right? So the intelligence over time that we're talking about, where it remembers, it recalls context, history, and all of that, you are the one that has to kind of create it by keeping that memory. Okay. And we're going to look at how to do some of that. So that's why state and memory matters, because without state, without memory, you will not be able to, sustain a conversation. Each time you have to come back and restart. Okay. Um, so let's look at some of the things, the definitions in when we're talking about state memory context. So state is a current execution snapshot. What that means basically is, where are we currently in terms of um, the current conversation that is going on, right? Where are we? That's what state is. And it is very important to know that, because that is needed for um, the context of the current conversation, right? Then other things, for example, state contains the variables. Um, for example, if there's a tool call, the LLM is going to extract the variables that are needed, or the parameters, or the arguments are needed for the tool call. So the state is going to hold that information. Then when a tool call is done, right, and you have a result that comes back from it, that is also kept in state. Then intermediate reasoning. So what intermediate reasoning is when you do a tool call and the LLM comes up with something based on that tool call. What it comes up with might still need additional tool calls. So it's not sent back as an immediate answer, but rather it is stored as an intermediate state or an intermediate reasoning, right? Which will wait until when you do further tool calls and the tool calls come back, then the new result from the tool calls will be used to further reason over that. So all of those things are stored in state, they're kept in state. So state is kind of a temporary place, scratch pad, if you will, where the results of reasoning are kept, temporarily while we are going through the loop, the reasoning loop, right? That's it. Memory is more of longer term, right? The information that is persisted across interactions. Maybe when you have finished a single reasoning, okay, some of that is stored, and then you start another session. In agentic workflows, basically you can ask the agent to do something. So think of a good example is you are refactoring a code base and using maybe Copilot or Cloud Code or something, and you tell it to do something for you. It reasons, right? It finishes that whole loop. That's one session. That's one interaction. Then you ask it to do something else, right? That is a new session, a new interaction. Between what you did the last time and now, there is still information that can be persisted between those interactions so that the agent in the next interaction is able to continue because it knows what happened the last time, right? So that is stored in memory. And you have two main types of memory, the way it is defined by, you know, the way it's defined in LangChain or in AI generally. You have the short-term memory, and then you have the long-term memory. So short-term memory is used to keep things like conversation, and all of that, right? While the long-term memory is used for longer term stuff, things that maybe you come back to tomorrow, next week, right? So things like your um, user profile, your user preferences, um, embeddings, right? And we're going to look at how embeddings or RAGs come into this, because effectively, you can actually use a RAG as a way of storing additional information or memory, longer term memory. And it's very interesting because this is what a lot of AI developers or development teams are doing currently, right? Where it allows you maybe some kind of conversation that you have had before can actually be stored as a document or saved as a document and embedded, right? And put in a vector store. So it becomes part of a RAG and can then be retrieved in future conversations or interactions. In fact, when we go into Mastra, right, and we start looking at what Mastra does, you actually find that Mastra even gives you um, this kind of capability, right, for you to actually take your previous um, conversations and store it in a kind of RAG, right? And that's what they call long-term memory. So it's very interesting. So that's memory, right? User profile, embeddings, and so on. Then context is, of course, what you are sending to the model right now. That's why we talk about context window. And context is made up of the current prompt, right, that you are sending, plus the retrieved memory, which will be stacked into another prompt, maybe a system prompt, or used to augment your the current prompt, plus a state, which contains additional information like we have seen here, the variables that LLM has extracted for two calls, the results from two calls, intermediate reasoning, and all of that. So all of this will be stacked, into prompts that are then sent as part of the context. So this context is now the total sum of everything. So in AI systems, the memory types that we talk about, we have what we call the ephemeral memory, right? The ephemeral memory is memory that does not last. It will quickly, you know, um, basically get wiped. In other words, once that particular interaction is done, that memory is gone. You can't get it back. And it's by design. So it's only for one single request, right? And it's normally such memory normally will be stored in a scratch pad. Okay. So a scratch pad is a good example. of that ephemeral memory. Then we also have a session. So a session is a single conversation, which basically means from beginning to end of a single conversation that you have had, right? That is a session. And a good example of that is the chat history, of course, which we talk about. Then we also have that's ephemeral memory, session memory. Then we have the long-term memory, like we said, across different sessions. So typically you store that in a vector database, okay? And then you have external memory, which comes from the tools, API calls, from the database, and so on. So examples are stuff that you get from the CRM and stuff that you get from the um, file system, from databases, and so on, right? So all of this can constitute memory, in the overall definition of memory. And when you talk of memory, memory is not the same thing as prompt, right? But memory can be used to augment or feed the prompt. And it's very important for you to understand that in the context of the context window, the size of the context window, right? If it is too much, then of course your LLM will begin to complain. So LangChain provides this, right? The conversation buffer memory, conversation summary memory, and the conversation buffer window memory, right? Now, currently, right, if you look at it currently, the way LangChain structures memory is slightly, um, they've kind of improved from this a bit, right? But generally, this is the way these are still available. The way LangChain handles memory now is you just have long-term memory and short-term memory, right? And you can decide how you want to implement that. But if you want other kinds of ways of implementing memory, you can use RAGs. RAG is a very good way of doing that, right? To implement your memory. And essentially, like when we're talking about the different kinds of composition of agents, which we are going to look at the tool augmented RAG, you let the LLM decide where it wants to pull its information from. Then I'll just talk about this again. We've talked about context window management. So remember you have token limits. Remember you also have cost. And remember you also have noise. So we have strategies to handle some of these challenges. A sliding window memory is a kind of a strategy where you, as your conversation continues, you always kind of take the latest N, you know, um, messages from the chat history, right? So you could say a sliding window of maybe 100. So once the length of the chat history is more than 100, the earlier ones before then will be chopped off, right? And we're not going to use them. We'll only use the first 100. That's sliding window. Summarization is where we try to manage the context by summarizing the first few messages, right? So again, there is the danger with summarization is that over time you summarize and summarize, then you have summarization of the summary. So you begin to lose the original context, the original content, because you summarize so that you still have some version of the original history, right? But when that also gets too much, you summarize that summary, right? In addition to maybe some new stuff. And you keep over time, if by the time you iteratively summarize, you get to a point where you lose the original context history. So um that is what summarization is. And summarization needs LLM, right? It is like saying my context window gets to maybe the conversation is now up to 100 messages in the stack, in the history. And at that point, the LLM has it's exceeded the LLM's context window. And we now say, okay, um, you know, let me compress it by summarizing the last um maybe 100. If it's 101 now, let me summarize the last five. So it's back to 95. I summarize the last five into a single message. So that summary of the last five, you need to basically take the last five first, send it to an LLM, right? Without any prior history or tool calls or anything. It will summarize that, and you then stack that up as your first message. It is now a summarized version of it. So you need LLMs to implement the summarization strategy. Then we have the retrieval-based context. This one is what I said. I think I said something like that earlier, where you can actually compress, well, not even compress, you can convert that conversation into a document, save it in a document, and store it in a RAG. That's what it is. You store it in retrieval memory. So you store it in a vector store, right? Store it in a database, vector store, index it, and then you throw away that one that you have stored. You throw it away from the conversation history. So, but you always have to remember, you have to let the LLM know that I have some previous, in the prompt, I mean, that we have some previous conversation that is stored in vector store in RAG. So if it needs historical, you give it as a tool call. You can make this tool call, right? And from that tool call, you can retrieve previous historical messages. So that's kind of retrieval-based context. You essentially convert the conversation history or a certain piece of the conversation history into a document that you store in vector storage, in retrieval memory. So then we have tool-only memory. So in this case, essentially all memory is now expressed as tools. Okay. And that means you have to store it, and then you have to tell the LLM, oh, here is a tool that you can use to retrieve previous conversation if you want to know more about the previous context. Okay, so those are some of the strategies that we would use to manage context window as it grows larger and larger, which will definitely happen, when when the conversations become very long. Now, so there is reasoning versus retrieval. Okay. In reasoning, we can look at it from a standpoint of three steps, right? First one is decomposition, which is take the problem and break it down. Then the second one is planning. Then work out, action plans, steps to be taken, right? The third one is decision making. Choose, make a choice, right? So those are the components of reasoning. And reasoning is not the same thing as retrieval. Um, Reasoning requires the LLM to essentially, well, reason, right? Decompose the problem, that's one aspect. Plan what to do, that's the second aspect. Third, make a choice or make choices. But retrieval, on the other hand, is fetch information, fetch facts, right? Or search through this document base that we have to find something that matches, or query an API call or a database call, right? Modern AI apps try to separate between reasoning and retrieval. And in most cases, you actually want to still reason over something you have retrieved. Retrieve, then reason, right? When we were doing naive rags, what we were doing was basically, okay, retrieve. Okay, retrieve, here's a context. Okay, and then answer me based on this context. But more modern systems now, the retrieval also helps even in the reasoning, or even in the planning, or even in the decision making, or even in the decomposition. The retrieval is not just, hey, answer this question, right? So that's one thing to take note of. So these are the steps that we would normally take in the process of a simple, straightforward agentic flow, right? You would receive the query, embed the query. This is for RAG, basically. Retrieve documents, inject into the prompt, and generate the answer. So what we will now do, what I want to for us to do is the tool augmented RAG. We are going to do um an implementation of tool augmented RAG. So let's get to it. After that, we will then go ahead to implement we'll go ahead to implement a simple endpoint, right? Very simple endpoint, because the next question is, how do I deploy like a smart system that pulls together all of this, right? So the first step would be to do tool augmented RAG. So I'm going to keep this. I'm going to keep this, and then I'm going to create a new. Um, okay, I think I. Um, okay, let's see. So let's start with a new. Um, okay, okay. So the first thing we want to do here, let's look at tool augmented RAG. So remember when we're talking about tool augmented RAG, what we said was you allow the LLM to decide what it does. So we'll first of all need to implement a RAG, because of course, since we are saying it's a tool augmented RAG, we first of all need to implement a RAG. And there is a very simple implementation of RAG, which we had already done. So I'm not going to rewrite it. I'll just take from where we did this, right? Under these indexes, so naive approach of the RAG without LangChain, manual RAG implementation, okay? But with LangChain, so it's very easy. We'll create a document loader, um, document loader. Um, I'm not going to worry about the web loader, but I can add that one later on. And then we'll use a recursive chunker, okay? And then we will then create embeddings. So we'll use I want to use Hugging Face embedding, so we'll use Hugging Face embeddings. Um, then we will do a vector index. I'm going to use Chroma. I'll just use Chroma. Um, with Pinecone, you could still use Pinecone though, but I need to go and create indexes and all of that. But let's just use Chroma. Then we can now create a retriever from Chroma. So a retriever is a special class that LangChain makes so that it's easy for you to pull um, data, right, um, from the vector database, right? You can plug it into LangChain's format, because LangChain uses chain format. So I create a retriever, and then yeah, I do have this helper function to format it. And we create a simple prompt to bring everything together, and then we chain it. So with this, we have a RAG chain. So this is a chain. I'm going to run it just to be sure that everything is okay, right? And there are two functions I will create. So the first thing is that we will need to um, if you look at this sequence, right, we have the docs, we have the embeddings. I can pull all of this into a single function, two functions, right? So the first function is to upload documents, right? And um, so doc is the document, which is, let's just take it as a string. Or yeah, let's take it as a string. I'm just going to do a naive thing. Okay. So to upload a document, I will of course we'll have the LangChain loaders. We'll do the document loader. Um, then we'll do the splitter. So the splitter is using the recursive character splitter. We don't need to create multiple instances of it. So I can just create it once. But then again, let me just create it in here. So it's okay. I'll create the embedding. So here I only need to create the embedding once. I don't need to create it multiple times. We're using sentence transformer and we're using the CPU. So of course, we'll also create the Chroma database. So I'll do that at the same time here. So we'll have a Chroma vector store. So we can call it index in this case. So let's just call it index. Then, well, so we can also create a retriever as well from this index. So index, okay. Right, so when we split the document, we can, right, let's update the index. So this is one way that LangChain allows us to basically, we upload the documents, Chroma from documents. What this does effectively is to take these docs and take the embedding, the directory, and it creates this. So I'm going to return this. Okay. So this is what we want to use in the future. All right. So this is a simple upload document. Now we'll build RAG or refresh the RAG. So we have a RAG chain that contains the retriever. Retriever always kind of changes. You pass it through the format docs. Um, let's me also create a function called build RAG. So again, this will encapsulate everything. So the first thing is um, can pass the index in. So let's do all of this. This is essentially doing that. So I'm going to explain this shortly, but we have done this before anyway, so I hope it's not going to be too difficult to follow. But because I'm kind of rushing, so I'm trying to get this all in. Okay. So build rag, you first of all have this function. This function doesn't need to be inside this function. So I'll put it out here. Prompt LLM. So we have a chat template here, and we just build the rag, and then we return the rag, return the rag chain. So this uses LangChain. To get the retriever, we would first of all um, essentially retriever is index dot as retriever. I think I copied that somewhere and I've thrown it away, but yeah, that's um you can pass in the top K here, I think. Let's see. You pass in the top K when you are getting the retriever. Okay, so it's search KWAgs. That's what I was looking for. Um, yeah, okay. And then that retriever we pass in. So this is complete the entire rag reduced to just two functions. Um, I hope it's as easy as this in JavaScript because it really does look very easy in Python. Right. So we have upload document. The one thing I need to check here is whether the index will keep previous documents whenever you do this, but it does look like it doesn't keep previous documents. So we'll have to modify this so that we can incrementally add. But this just looks like, hey, I have a whole bunch of documents and I use it to make a vector store, right? And then, but it should be possible to update that vector store. Then build rag essentially creates a chain, right? And returns that rag. So that's just the rag part of it. We still need to do the, so let me put in my .env. Um, and then let me put in my properties, my .m variables rather. Okay, so okay, I forgot something. LLM needs to be passed in, so I can pass that in as a model, and or perhaps just create the model here. We could do that as well. Um, yeah, let me just let's create the model here. So it's easy to create the model. Oh, let's do it externally. So yeah, I need to install all the installables. So pip install LangChain community um LangChain no comma LangChain text splitters. LangChain core is already installed. ChromaDB, Hugging Face. Yeah, okay. So we install all of those requirements. and this all should go away, and we should be able to get everything. Okay, so while that is running, so this is just the rag part. Okay, this is just the rag part. Um, build the rag. Okay, so don't have a lot of time to type a lot of stuff, but yeah, so this is the rag part. Now the tool part. So you see tool augmented rag. So you have to first of all do the rag, then you do the tool. Okay. Let me just confirm that this works. I need a couple of documents here. Um, so I'll just do um oh yes, so let's do this. Right. Um Again, this is just a sample of how you do that. You could have a lot more documents, right, than just this. Okay, you should have a lot more documents than just this. And this loader should have a lot more files, right, than just this. But for now, we just go with very simple steps. So the first thing is to upload the document. And this is a file name. We'll still use the same file name. And I'm going to bring some content in here. Uh, okay, so let's just take LangChain. Okay, let's just take LangChain migration guide. I hope this will not be too big, too large. So this is a very good opportunity. Let me use the agent page, which actually has a lot. This is one good example because this is a large document. So we will look at chunking. Like it's really going to help us understand how chunking works. So I'm just going to go to, let's see, LangChain's overview on agents, copy this whole page. It has a lot in it and see how well the chunking works. Um, so even though it's called engineering manual, but there are 568 lines in this document. Okay, so all right. So when we run this, we can even see the number of chunks. Um, yeah, but let me just run this. Okay, I need to run everything. So I've done the pip install. This is okay. This is okay. Um, vector stores, run the embedding, run the function definition. So sentence transformers needs to download as usual. Run the upload document, then run this that does the rag building. Then now we upload the document. So you can see this does a whole bunch of stuff. I should have assigned it a value, right? Is a vector store chroma. I should have assigned it a value. So let me do this. Index equals. We can play around with this index to see what it has. So for example, we can check like how many documents are in the index dot. So we have embeddings. You can check out embeddings. You can do search. You can update documents. You can update documents, and you can add documents. So yeah. So embeddings is the embedding uh, vectors. You can do search, right? Which is a similarity search. Now you can specify a query and how to use agents. So search type. Um, so this is a type of similarity search which we can say cosine of similarity search. So you see all of the chunks that we have, how to use agents. So you see I'm seeing repetition here anyway. So index allows you to do it's good to go and check that in the LangChain documentation. You're going to see where it talks about vector databases and so on, indexes, retrievers. So a retriever is an interface that returns documents given an unstructured query. Yeah, so a vector store, what we get is a vector store, but retriever allows you to basically run a query on the retriever and it gives you something. You can check the retriever's um, API, right? And you see. So take some time and look deeply at LangChain. It has a lot. Okay, so we have an index. Now we can take this index and because we say build a RAG based on an index and a model. So I'll create a model and then I'll use that model to along with the index to get a RAG. So to get a model, we can just model equals chat open AI and we specify the model is Nemotron. I basically don't need to redo this. I can take this from React where we had already done a similar thing, just so it's faster. Um, so it's faster. So okay. Of course, I need to import the chat OpenAI from LangChain OpenAI import chat OpenAI, and I need to install LangChain OpenAI. So pip install LangChain OpenAI, and OpenAI is already installed anyway. But so we install LangChain OpenAI, and that will give us this. So we import, and then we create the LLM, and then after creating the LLM, oh yeah, okay. So I needed to do this. I don't know if I put in all my this. Okay, I did. So I need to import OS as well. Okay. Load.env. Okay, from .env. Yeah. Okay. All right. So we have LLM. Now we create the RAG. So build Okay, so we can just say rag equals build rag, and we specify the index and the model. So we get the rag. This should work without any problems, hopefully. And once we get the rag, then we can just query the rag by saying rag.invoke. How are agents created? And the rag should give us that agents are created using the create agent function. Right. Okay, so we now have a rag that we have created. So what is tool? Um, how do we now bring in the tool to assist with the rag? We can define that, and we've done it already, so I'm just going to bring it up. We can define that as a tool, right? And um, well, this is it, right? We define this as a tool, and how you define the tool is, of course, from langchain dot tools, import tool. Um, then we will do tool, and then we'll do a function of um, yeah. So remember, this is a tool definition, so we need to tell it. Um, okay, okay. Well, I'll just go with this. Useful for when you need to answer um, questions about the engineering manual. Right. So we do this tool, then we create an agent. So to create an agent, we import um, from langchain dot agent import create agent, right? So to create agent, you just need an LLM and a tool called the LLM that will handle. We could use the same LLM that we use for the RAG, right? Um, but the beauty of it is we could also use a different LLM. So there are LLMs that may be optimized for RAGs, LLMs are optimized for agentic. So we create an agent equals create agent. So we specify the tools, we specify the LLM. It's actually not correct to say LLM. Is the correct thing is to say model. So all of this AI they have not been, they're kind of trained on old LangChain versions, so they keep giving the wrong stuff. I don't know about verbose. Let me see if that works. Obviously not. Okay, I need to run this RAG too. Okay, and then I run this. Um, yeah, I don't know about verbose. Verbose is for when you are defining, um, when we were defining the plan and execute agent. That's when we use verbose. All right, so you have an agent, you have if you have a model, the LLM you've defined, and then you have a RAG tool that you have defined based on the RAG, right, which you can invoke using a query. And that's it. You have the agent. So this is a tool enhanced, you know, RAG, basically, or tool augmented RAG. So we can now ask questions of the agent that may not necessarily need the tool or the RAG, and questions that may necessarily need the RAG. So that's the beauty, right? Okay, so we have messages. When you're invoking an agent, you use messages, and then you can stack your messages here. So you can use role user content this, or you can use a tuple user and content, or you can just use human message, or you can just put it in there. Okay. So if I now do human message will need me to still put to need me to import, but that's not a problem. The agent is now, um, oh yeah, it's going to print out everything. So you can see here, you had the human message, how our agents created. So that's the first. Then the AI message comes back with a tool call. You can see content is 0. It comes back with a tool call, and tool call, it knows that you can call this RAG tool. So it sends the RAG tool this query, how are agents created? Same query you gave to it, right? And then that's it. Then the response from the agent, it does a tool message, right? And it gives you the response based on the response from the RAG. So you can now see the RAG takes the response, and the agent takes the response from the RAG and turns it into a tool message. And that tool message is then sent back to our agent, and the agent uses it to generate. Of course, because I did not assign this to a value, so I can say result equals this. Then when that is done, results um, messages. Remember, it is the last message that we want, right? Dot content. We can even put that in the markdown. If we didn't have markdown, import from IPython, import markdown. So we'll just put that in the markdown. So this is okay, I need to run this first before I run that. Agents are created by using the create agent function. This function builds. So you could add more tools, API calls. So this is now a tool augmented RAG where you built a RAG. So in this same thing, I built a RAG from LangChain. And then after building the RAG, I then built an agent. I built a tool that will call out to the RAG. Then I built an agent that is given that tool. So whenever the agent needs that tool, it is going to do this. Now, um, oof, I lost. Okay, I thought I lost the runtime. Okay, so now I could also do another agent call, right? But this time around, I am not um I'm not asking questions about agents. I can say something like give me a list. Okay. I like this. I always say what um I don't want to ask it something that it will ask for. Okay, so let's say what is your name? This is interesting, right? So this is not going to require a tool call. So let's see what it gives to me. We could just print out the result. Let's see the entire result, what it looks like. So you can see that it's human message, that's my message, and there is just one AI message. You can see there's no tool call here. My name is Nemotron Nano, and I was trained by NVIDIA researchers and all of that. You can see no tool call. Now let's do something else. Let's ask the agent question on yeah, so something like what can I use an agent to do? And let's again see. I'm going to let the whole thing drop so that we can see. This is now reasoning, so it's React. Basically, it's cycling maybe like 2 or 3 times. So you can see in this case, because it still has to do with agents, it's still going to ask for the tool call. So the second response, it asks for tool call, and the tool call is still the same um, thing. RAG tool, what can I do? The tool message response. So you actually get this tool message. An agent lets you combine a language model. So this is the response from the tool call, right? And then AI message gives me this. Not only that, it even highlights it with its own markup and everything. So if I were to put this in Markdown, um, yeah, so this is the content that it gives back to me. I'm going to copy it and just put it in Markdown. And yeah, it may not look so clean, but this is what it gives back. So that's it. Tool augmented RAG. The last thing I would like us, we might not have enough time because we've run out of time, but I wanted us to look at what next, right? How do you pull all of this together and create a backend that has AI? What are the considerations when creating a backend? So we'll look at those when we meet next week. Okay, that's it from me. Are there any questions or comments?